Hello and welcome to Haybridge Maths Department Year 2 Pure Chapter 3 series. Previously we've been looking at arithmetic progressions, then we looked at arithmetic series, then we looked at geometric progressions, and today is the turn of geometric series. So let's get started. Let's have a look at what a geometric series is first of all. Okay, unsurprisingly, if you think what an arithmetic series is, and geometric series is a sum of the terms of a geometric sequence. So here is a geometric sequence. If we just get the pen on, 3, 6, 9, 12, and 24, but you've got a sequence. And then the series is 3 plus 6, 9 plus 12 plus 24, which is the series. And if you were so inclined, you could work that out if you really wanted to. Now, we could do that by brute force and just add up each term, go 3 plus 6 is 9 plus 9, which is 18, and work it out like that. But if you've got a really big series to sum up with some really massive terms or some really small terms, you want a formula. And instead of giving you a formula, we've given you two. And here they are. A is the first term, as it always was, and R is the common ratio of a term, the number that you multiply to get from term to term. Now we have two different formulae, and they both work, but just as a rule of thumb, we're trying to use the top formula if our value of R is less than 1, so that the geometric sequence is decreasing, and if R is greater than 1, so something we have to watch out with viral infections, but if R is greater than 1, then we use the bottom formula. The only reason for that, I think, is that the top formula you're going to get, if R is less than 1, you're going to get positive numbers out of there because of 1 minus R, and if R is greater than 1, then you want to use the bottom one again, just to make it slightly easier. Either formula will work, but it just depends on how what your value of R is, which makes it easier to use. Okay, moving on swiftly. Right, here we have some geometric series. What we're going to do here is we are going to work out what they're equal to using the formula that I have just shown you there. So if we look at A, first of all, we can see that A, we have A equal to 2, R is 3, we're multiplying by 3, and there are 10 terms because the question says so. Okay, so let's use the formula Sn equals A brackets Rn minus 1 R minus 1. And if we just flunk some numbers into that, then you have 2 and you have 3 to the 10 minus 1 over 3 minus 1. Well, the 2's will cancel. You'll get 3 to the 10, take away 1, which is the rather lovely 59,048. All very straightforward. Effectively, you're subbing numbers into a formula, sticking them into your calculator. What could be difficult about that? But let's have a look now at part B. Now, in part B, we don't know how many terms there are. We just know that it finishes at 1. So our first thing that we have to do in this is work out how many terms there are. So let's get on and do this. By the way, I should have said at some point at the start or somewhere, don't forget to pause repeatedly throughout the video. Make sure that at times that you pause, take notes, then watch. It's better to take notes once you've listened to me whittle on for a bit and go back and then make the notes, then try to make notes as I waffle on about things. Okay, so anyway, part B. Now we saw that A was equal to 1024. Then R, we'll just look back up here. We see that we're halving each time, but we're also swapping between negative and positive. So you've got R equal to minus a half. Okay, and then N is what we don't know. And before we can start sticking things into a formula, we need to work out what N was equal to. So if you remember from last lesson, we had this formula, UN equals AR to the n minus 1. Now we know that this last term is equal to 1. A was equal to 1024, and whoops, R we know, and that is minus a half. So we're going to go to n minus 1 over times the next square. Now, quickly rearrange for 1 over 1024. Everything seems to be going smoothly. What's so hard about this? It's all very easy. And then we hit this subtle little point here. I'm just clearing some space to do some writing, but I just want to show you something here. We've got on the left-hand side a positive number. On the right-hand side, we've got that minus a half. Now, the only way that we are going to be able to raise that minus a half to a positive number is if this power here, the n minus 1, is even. It has to be even, that n minus 1, for that to happen. For instance, if I have minus 2 and I raise it to the power of 1, I get minus 2. If I raise minus 2 to the power of 2, I get 4. It's positive. Minus 2 to the power of 3, minus 8, minus 2 to the power of 4, 16. So it always flips-flops between positive and negative, depending on whether it's odd or an even power. So that means that n minus 1 must be even. So n minus 1 must be even. But here's the other thing. If I have, say, minus 2 squared, I get 4. But that's the same as 2 squared, which is 4. Minus 2 to the power of 4 is 16, which is the same as 2 to the power of 4. So when n is even, what happens is that it's the same as if you didn't have the negative there at all. So we might as well just write therefore, or not quite therefore, that implies that a half to the n minus 1 is the same as 1 over 1024. Sorry about that, that's a bit nasty. To throw that in straight away, I think it's a little bit tough, but the rest of the question is a little bit easier than that. Right, okay, if I've got a half to the n minus 1, that's the same as doing 1 to the n minus 1 over 2 to the n minus 1. Now, 1 to any power is just going to be 1, so effectively we end up with 1 over 2, 4 equals 1 over 2 to the n minus 1. And then we have 1024 equals 2 to the n minus 1. Now we could do logs here, or if you're feeling you know a lot about computers, or you just want to play about with your calculator for a bit, you can quickly see that n minus 1 must be equal to 10, and therefore n equals 11. Like I say, if you want to, you can solve this here using logs. Personally, I did it through inspection. It's your call. Now, you'd think we'd finish there, but we haven't. If you remember, the question all the way back here was find the sum of the following geometric series. Right, okay, so we've found out that there's 11 terms. Just spotted something when I looked at the question and just thought, well, if you knew that 1 was going to be the last term and you knew that it was 2 to the 11, I could have spotted that straight away, but you know, hey ho. Like I say, if you don't spot the n minus 1 is equal to 10 thing, you can do that through logs, and I've done plenty of examples where we've done that. Anyway, right, okay, let's just work out some of the 11 terms. So you go S11 equals A 1 minus R to the N over 1 minus R, and whoops, let's push that up a little bit there, and let's sub in our values. You've got 1024 1 minus half to the 11, all divided 1 minus a half can be 3 over 2. Plug that all into your calculator and you get 683. Lovely. Right, suggest you have a bit of a pause there, make your notes, then come back in a second and have a go at these next 2 questions that I've set you. I should say, by the way, that these examples are a little bit easier than what I have just done there. So have a go at these 2 examples here. Okay, I'm just looking ahead there. Right, let's have a go at part A. Now we are looking at in part A, we have A is 1, R is 2, and N is equal to 8. So we want the sum of the first n terms, A R n minus 1 over R minus 1, and the sum of the first 8 terms, we've got R times 2 to the 8 minus 1 over 2 minus 1, and if you do that, then you get 2 to the 8. Subtract 1, and if you get that, you get 255. Of course, the 2 minus 1 on the bottom just goes to 1, so that's okay. All right, okay, and then part B. On part B, you should have done A was 32, R equals a half this time, and N equals 10. So this time you want to go to the other formula. So you want to go to the 1 minus R to the N over 1 minus R. Okay, and at this point we sub in, so we go sum of the first 10 terms, you've got 32, 1 minus a half to the 10, 1 minus a half, which is a half. So put that all into your calculator. You're going to get, if you just bear with me for 2 seconds, you're going to get 64 times 1 minus 0.5 to the 10, nothing like doing this on the fly. And if you do that, you should get 63.9 to 3SF. Or 1023/16, if that's the way you want to write it. Okay, right, let's move on to another example. Right, here we have a series that keeps on going as 1 plus 2 plus 4 plus 8, and it keeps on going until your sum gets bigger than 2 million, and then we stop. So what we need to do here is work out what n must have been equal to for that to happen. So if we start off with a is equal to 1, r is equal to 2, and we know that Sn is bigger than 2 million. Okay, so you've got a bracket Rn minus 1, r minus 1 is bigger than 2 million. So if we just put in our numbers, we go 1 times 2 to the n minus 1 over 2 minus 1, which we'll write it down for now, is bigger than 2 million. Right, clearly the 1's will cancel, so and you'll end up with 2 to the n minus 1 is bigger than, I'm tired of writing out 2 million, but it's bigger than 2 million. Add on the 1, and great, I've got to write 2 million and 1 now. Right, okay, why do we choose such big numbers? We are going to take some logs, of course, so we've got n log 2 is bigger than log 2 million and 1. So n is bigger than log 2. I'll be glad when we work this out on our calculator and I don't have to write 2 million and 1 anymore, over log 2. So n is bigger than 20.9. So the least value of n is 21, because n has got to be clearly an integer, positive integer, because it's a number of terms. Okay, so once again, pause the video in a second, make notes on this, and then move on, and you guys have a go at this example. Okay, so pause, have a go at this, and then I will go through it well, whenever you're done, really. That's a great thing about videos. You can take your time, do the video now, go away and have a cup of tea if you wanted to, or get on with it, it's your call. Anyway, I'll get started, because, yeah, why not? So we've got a equals 3, r equals 2, and this time we know that the sum is bigger than 1.5 million. There you go, another massive number for me to scroll out on this. Now, some of the first n terms, since we're using r bigger than 2, we're going to go r is bigger than 1, rn minus 1 over r minus 1 is bigger than 1.5 million. Why can't I just change like 15 or something like that? Right, okay. Let's sub in a number. Let's sub in 3, and we'll have 2 to the n minus 1 over 2 minus 1 is 1.5 million, and then you've got 1.5, and you've got 1.5 million. So a bit of jiggery pokery, and you get 2 to the n is bigger and slightly smaller, 500,001. Right, taking logs, yet again this pattern should be quite familiar to you by now. You have n log 2 is bigger than log 500,001, so n is bigger than log 500,001 over log 2. So n is bigger than 18.9, so at least n is 19. Again, lots of writing here, so copy all of this down into your notes, making sure you get it all down, and then we'll go for another example. We've done the examples slightly different order to the book. What I want to do now is look at a famous example of a geometric series, and then we will go for the proof. Now, you probably heard the story when you were younger about somebody somewhere. It tends to be somewhere in Asia, though I've heard it told about somebody in India, somebody in Iran, somebody in Far East Asia. It tends to be somebody of lowly rank who does something really nice for the king or emperor or queen or somebody of high rank. And the king, queen, stroke emperor goes, "Oh, you've done brilliantly there. Thank you very much. Whatever you've done, brilliant, lovely, cheers, much appreciated. How can I reward you?" And the person of low rank, the peasant, turns around and goes, "Right, I'll tell you what, give me a grain of rice on a chessboard, on the first square of the chessboard." And the king goes, "Yeah, right, fair enough." And then the peasant goes, "And on the next day, give me 2 grains of rice on the next square on the chessboard. And then on day 3, give me 4 grains of rice on the chessboard. And then on day 4, give me 16. And the king's thinking, what an idiot. That's easy. I mean, 16 grains of rice, 32 grains of rice, 64 grains of rice, tiny. And all I've got to do is fill up the chessboard." And the king goes, "Yeah, all right, that's a deal. You know, you did me a favour. Thank you very much. I'll give you that reward if you really insist." And off they go. And then it all starts going well for the king. Then after about a month, things start going really, really badly wrong for the king as he starts to run out of rice. And like in the end, like there's more rice needed than there is in the world, and either, depending on your version of the story, the peasant has his head lopped off, the peasant is like rewarded fully, and the king repents his ways. I don't know. I've heard so many different versions of a story. Well, clearly none of them are true, but I don't know which one is the original. I think you've just got to kind of go with what you fancy. You choose whatever you want, which way ever you want the story to go. You believe that version, right? Okay, so how are we going to do this? And I'm going to do it without using the formula. So we're going to work out the first 64 terms. So we are going 1 plus 2 plus 4 plus 8, and we keep going until we get to the penultimate square, which is 1 times 2 to the 62 plus 1 times 2 to the 63. You can't see that I have struggled right next. That's a bar for where I record, which hopefully shouldn't be visible when you're watching this. But anyway, so there's the sum there. So you've got it there. Now here's the trick. To get from term to term, we multiply by 2. So what I'm going to do is I'm going to take that complete sum and multiply it all by 2. And this is what I mean. So I get 2s64. Now 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 16. Now 1 times 2 to the 62 is 1 times 2 to the 63. And 1 times 2 to the 63 times 2 is 1 times 2 to the 64. So what I am going to do now is I'm going to take this equation here and I'm going to take away from it this, which is not really equation, this sum here. So I'm going to get 2 s64s minus 1 lot of s64. Now, when I take the one away from the other, I'm going to get the 2's here will cancel. The 4's cancel. 8's cancel. And we keep on going. The 1 times 2 to the 63 cancels. And that would have cancelled with something before. So we'd have been left with the 1 times 2 to the 64. And we'll be taking away that 1. Now let's have a look at the left hand side of this sum that we've just created here. 2 lots of s64 minus s64, 1 lot of it is just going to be 1 lot of it. And on the left hand side you've got just 1 lot of s64, but on the right hand side you've got 1.84 times 10 to the 90. Okay. So that's a lot of rice, and more rice than there is in the universe or something. Okay, let's have a look at proving the actual overall formula for the geometric. Now I'm going to go with the version of when r is less than 1. Obviously r can't be equal to 1 because you'd be dividing by 0, which causes a whole manner of like black holes and problems. There's a slight bit where, depending on which way you choose to go, it lets you pull out one or the other formula. It's very easy to do the other version of a formula, and I will show you what I mean when that happens. So let's write out our Sn. So Sn is a plus ar squared plus arn minus 2 plus arn minus 1 as our last term. Okay, last time, if you remember, we multiplied through by 2. What I'm going to do here is multiply everything through by r common ratio. So here I've got AR, I've got AR squared, I've got AR cubed, and we keep going. Now A to the RA times R to the n minus 2 times by R is going to be ARn minus 1. And then the last term, Rn minus 1 times by one more lot of R is just going to go A times R to the n. Right, next thing that we're going to do is we're going to take away the bottom, the top from the bottom. So we're going to do RSN minus SN. If we did it the other way round, so we did SN minus RSN, then you would get the other version of the formula. I've just noticed that I've worked it out the wrong way. So actually I will do top take away bottom. So we'll do, in my notes, when I did this I've worked it out the wrong way, so let's do it this way. So we'll do SN minus RSN, and then if we do that, then we're going to be left with A, because this is left over, and we take that away, and we take that away, and the thing there, take that away from there, that's going to vanish, but we can't see the term. That's vanishing. And we'll look for that. So we've got a minus a times r to the n. And then we take out a factor of Sn. So we've got Sn 1 minus r equals a brackets 1 minus r to the n. And we've got Sn equals a brackets 1 minus r to the n over 1 minus r. And that is the correct version of the way that we use it, but we'd put it at the top. If you want it the other way round, just do the RSN minus SN. Okay, so that's been geometric series. What I'd like you to do now is, of course, pause, take down this proof, and make sure you make all the notes throughout the exercises, and then could you have a go at exercise 3D. Thank you very much. Goodbye.